Okay, and this is so okay. First of all, the reason why I wanted one LLD and HLD is because it gets a bit boring. It's difficult to connect on the LLD part, right? A lot of design patterns, even if you know, probably you might not use it. So that's the reason I want to mix it up so that people don't get bored and like they don't just think that okay, this is not useful and they run away, right? So this is the reason I'm trying to mix it up. This is going to be the first class for HLD, and I'm going to talk about distributed systems. If we have time, probably also cover cap theorem. And yeah, so this class is gonna be about those things, the characteristics of distributed systems, and then basically about cap theorem, if time permits, right? Okay. And I would want to like have an interaction with you guys while having this class. So feel free to answer when I ask any questions, right? So how many of you guys have designed, like have worked on your local, like having a server or any kind of application work on your local and understand taking it to production? Like your local code goes and gets deployed into a production, and understand how does it look like? How many how many instances of server if it's a server-based application, is how many instances do you run? Do you only run one instance or do you run more than one instance and things like that, right? So okay, somebody in the chat said something. Okay, yes. Okay. Yeah. So how many of you guys have experience with this whole thing? So I think most of the web developers would definitely have experience about these things. But I just want to know, like, how many of you do a development on your local laptop, which is a single instance, and then deploy it to prod? I see one thumbs up. Two. Okay. Okay. So let's talk about resources in a single instance, right? So when I mean single instance is basically take this as your computer or your laptop, right? This would have certain number of CPUs, right? So if you remember in the good old days, we used to have one CPU. And this was way back, I would say in the 90s, you would have like one CPU unit, which is basically means that it was one CPU as such, like complete one CPU. Now they're divided into something called as multiple vCPUs. So you will have something like 2 vCPUs, right? Or 4 vCPUs. We do have the RAM and the other things, but like we have like multiple vCPUs and things like that, right? Even in a laptops as such. Do you guys, or probably, I think most commonly in outside of the tech world, people call it as core. Or like I think 2 core CPU or 3 core CPU, not 3, 2 or 4 core CPUs, right? 4 cores. Okay. Can somebody tell me what does this 4 core mean? And why do we need that? Why don't we have only 1 core in our systems?
4 cores means 4 processors.
Yeah, and why do we need multiple processors? Like, why do we have 4 processors instead of 1?
Yeah, it's better to do 4 tasks at a time rather than 1.
Yeah. Okay. Okay. So you're right. So how many of you guys understand what is a process and what is a thread? Okay, Sumit says yes, and I don't see Anil says yes. Okay. Okay, so probably I would want to discuss process and threads in detail, but probably for this class, I'm just going to keep it simple. So any application which runs probably is running as a process, right? So for example, I'm running Zoom on my laptop, right? Or I'm running IntelliJ on my laptop. So these two would basically be running in 2 different processes. And you can basically do is you can run a command. If you're on Linux-based system, I would say you can run something like a top command. Or if you have some utility installed like htop, you'll probably go and see like a lot of like processes running. It would basically talk about a lot of processes running and things like that, right? So you can think of this that in a system, you would be basically be running multiple processes. So if you're opening up 5 different applications, right? For example, I've opened up Chrome, right? I have also Zoom, and I'm like working IntelliJ, right? So do you know how these multiple processes are going to run on the same system? Anybody has any idea? So like I'm running three different applications. Whereas suppose if I only have one CPU or one core, how will it work out?
Scheduling.
Yeah, but this is something called as
Scheduler.
Yeah, this is called as multiprocessing or multitasking in normal terms. I think if you refresh your mind, probably going back to your OS classes back in college, right? So what this basically means that you can run multiple applications at this or multiple processes at the same point of time, even in one CPU. The only thing which happens, and this happens really fast, right? The CPU would basically be giving resources or the yeah, I mean, in terms, you can think about this, that there's going to be an OS level scheduler, which is going to give you like CPU to this process once, and then this process and this process. And they're going to keep on basically scheduling, okay, do this, then do this, then do this. And it keeps on like basically rotating between these tasks, right? So it gives like 5 seconds to this task, then 5 seconds to this task, and this 5 seconds to this task or this process as such. What happens is, because for us humans or for this, like we will not be seeing, even though multiple processes are running and the process on which we are is getting paused for a bit, but we will not be able to like it's so, like I would say it's so fast that you will not be able to like see, and I mean you will not be able to feel that latency basically. So you will not feel that your system is getting stuck in that process, because it's going to schedule in that, like it's so fast in that, right? For example, think of it this way. It's going to give you 5 milliseconds to this particular process, and then the next 5 to this, next 5 to this, and then goes back to the like the first one and things like that, right? So it's scheduling and it keeps on doing that, right? This is how you run multiple processes into a single core or things like that. So this works, but this works up to a certain limit, right? Now people want to open 10 different applications, 20 different applications. You want to download in the background and you want to watch a video on Chrome or do something else, right? So once these kinds of requirements start kicking in, it was hard to do all of these in one CPU or one core, I would say. So what the microprocessor designers came up with is like, okay, so we'll break down the CPU into multiple cores. And what's going to happen is we are going to give, like the same thing is going to happen, but now you also have multiple cores, right? So you are able to do multiple of these things at the same point in time. So suppose I have like 2 cores. At the same point in time, I can run process 1 and process 2, right? And you can obviously do multiple processes on each of these, right? But I'm just saying, like if you have like an 8-core CPU and you're running eight basically processes, you are able to do like 8 of them parallelly. So you're basically no process is waiting on for CPU and things like that. Okay. Okay, is this clear? And I'm just gonna be taking at the basic level. Okay, yeah, Sumit.
So when we have multiple cores, so is it only for the distribution of different processes, or different threads of the same process can also utilize multiple cores?
Yeah, so it depends on the architecture, I would say. You can do that. So this is simpler to understand, where you say like, okay, one process is run on one core as such, but that's not always true. You can do that, right? So a process can be divided into multiple cores or like a multiple I would say same process can have multiple threads, where one thread is being processed by CPU core 1, and whereas the other thread is getting processed by CPU 2 as such. So it's all possible, it's all doable. For the sake of simplicity, we want to like keep it as like, okay, this is the way it works. But yeah, it's all possible, right? So basically, now I'm going to talk about threads. So in a process, right? So if you take an example of like a Chrome, right? So if I'm running something like a Chrome on my laptop, this Chrome, I have multiple tabs open. And this is basic assumption which I read about in the past. I don't know whether something has changed on the Chrome side of things, but initially, like they used to do multi-processing, which basically means that each tab which you open, right? For example, in tab 1, I have like something like a Hotstar open. In tab 2, I have some other application open. And in tab 3, I have another application open. Basically, they were creating multiple, each of them would have like a process. So process 1, process 2, and process 3, something like this was there. But most of the time, because, and this is the reason why Chrome gets a lot of criticism, that it's very, it's very resource intensive. And this is what happens, right? Like a lot of these processes are running, and if you open 10 tabs, 10 processes are running. So what happens is, if you go and look at run your top command in your laptop, or I don't know the Windows equivalent of it, sorry about that. But if you run it on a Linux, you would find like it's taking high number of CPU, and like it's basically taking 100% and something like that, right? 200% and things like that, which basically means that it's consuming a lot of CPU, and it's basically hogging everything for it. And if you have any other applications running, probably they might not be getting enough CPU time as such, right? In general, if we don't take an example of Chrome, and if we move into something else, right? For example, let's take an example of something like an application where you download stuff and you do something else, right? So suppose I have a okay. Let's take an hypothetical example. For example, we are working on Zoom, right? Yeah. Yes, Sumit. Sumit, do you have a question?
But I like my experience, I thought that Chrome is very light and better than others.
It's not.
Know. Okay.
Yeah, it's not. I mean, if you want to read, go ahead and read up. Okay, I can do one thing. I could.
No, sure. I mean,
yeah, probably. I think I'll probably share some links after this class, because I think
just
but pointing it out, right? Like it's really bad, and it is one of the very heavy criticisms of Chrome as such. I don't know whether sorry, Anil, you say something.
Yeah, actually what he said, that Chrome is light because it is considered light because they are using V8 JavaScript engine, so which is very light. So that JavaScript engine, as Internet Explorer was using, that was heavy, but the JavaScript engine used by Chrome, it is very light. This is V8 JavaScript engine. That's why it is considered light. But in terms of memory, yes, it is a very, it takes very much, too much memory.
Yeah. Okay. Yeah. Uzeen.
Yeah, actually, as you mentioned that one CPU, one process takes one CPU at a time to run itself. So does it applicable for thread also? Thread also take one CPU at a time or take a part of CPU?
Yeah. So I would say, like at any point of time, right? You think about this, right? You would not want to. I mean, if there's a processor, right? You would want to give the whole processor to this particular thread or something like this to process, right? It's not that you can divide it into some things. There are like if you look at JVM and things like that, they build an abstraction on top of this, where they would spawn out things on their own. So you can think of it as one process inside, like trying to make multiple threads and things like this to do some processing as such. But most of the time, or I would say, I need to look into like this. There's any exceptions like this, right? But when like even a single thread would want a whole CPU time as such, or one CPU core as such, you would probably not divide it into any more. Like you cannot say that, okay, this core one I can give it to 3 threads. It's not how it works. It would seem like it, because from the outside, as this scheduling is really fast, probably you'll not be able to like from the naked eye, you'll not be able to recognize this. But it's always going to be at any one instance of time, any one thread or one process. It's going to take like the whole core as such. It's not going to be able to subdivide and use it as such.
Then thread and process is same.
Yeah.
Like they are consuming a single core.
Yeah. So the difference is, okay, let me talk about this, and I think the answer would be clear in this particular session.
Sure.
Okay. Yeah. So if I'm running Zoom, right, Zoom would have like, I'm doing something like a screen sharing, as you can see this, right? I'm doing a screen sharing. The other is like I have a camera on, right? So you can basically see me, and probably it's doing something like a streaming of a video and things like that, right? So if you think like the same process is doing two different tasks at the same point of time, right? How you can accomplish this? And to be honest, I'm not really sure how does Zoom does that. Like, is it like spawning up 2 different processes or spawning up 2 different threads? But one way to do this would be, if I have a process and I will call it pzoom, right? I can have two threads. Thread one is basically T screen sharing, and the other is like T camera. So I could spawn multiple threads in a process, and I could basically make them work parallelly as such, right? So at any point of time, when for like accomplishing multiple tasks within a process or things like that, right? You can do is you can create multiple threads and make them run parallelly. So the same thing, like you can run multiple processes the same way you can run multiple tasks, threads. The only difference, or one of the differences being, is threads are generally tend to be lightweight as compared to processes. Why? Because process will take the whole memory, it will have their own memory, and it will take like spaces and things like that. So it comes up with the whole thing, like, right? The process would have their own memory. It will take, it will store some like footprint, right? And things like that, thing. Whereas threads can basically do is they can share memory as such. So if two threads are running, they could basically share the same memory. And this is where we generally have those issues with concurrency and like threading, multi-threading and things like that, right? When people say that it's not thread safe. And like, have you heard about these terms like not thread safe? And if you remember the example which we shared on singleton, right? Why are we trying to take, like, why did we have a double lock there? Or why did we want to say that only one thread should be entering this particular punch? I mean, I would say lines of code, but I think there's a term for it. I just slipped my mind.
Section.
Sorry?
Block.
Critical section.
Yeah, section of code, or
Block.
there's a better word, right? When you write some places and people call
Critical
it.
section.
Yeah, critical section is a multi-threading term, I would say.
Scope.
Block of code. I would say like block is probably a word. The right word would. I think it's something different, but yeah, you can say like some block, right? So when you say like when you want to say something like this, right? That this block of code only one thread should enter at.
Critical section.
Yeah, you can. Yeah, the concurrency term is critical section for this. The more generalistic term is basically a block of code, right? So when you say that, okay, this is, you would want only one thread to enter into this, right? Why? Because if two threads enter into this, they might change the state in such a way that now you don't know how it's gonna go. After like coming out of this block, you don't know what the behavior would be. So those kinds of things, right? So coming back to the discussion, right? Thread is lightweight because they can share memory between them. Like two threads can share memory, and we have seen that, right? If in singleton also, when we created that static instance, basically two or more threads, if possible, if you have more than one thread, would be able to basically use that same memory, right? Tap into the same memory and use it. Whereas in process, because there are two separate, I mean, I would say like something like this, right? Process one and process two are completely exclusive. So they would not have any, like, they would not share anything as such. They would have their own space and things like that, right? So this is the difference between threads and process. If you want to do a simple task, and if you want, I mean, if you want memory sharing, right? Sometimes you do want memory sharing. And so for those use cases, threads are better. If you have like two different processes, you can think of this as like something which is totally different from something else. You would want to have like two different processes running. Or if you feel that I don't want to share any memory and things like that. But you should also be careful that it's going to be resource intensive, because it's going to have like its own memory, like it's going to allocate its own memory and things like that. Probably it's going to be two separate entities altogether. In threads, think of this. Okay, I will take a real world example. So suppose, and this is from the web world, suppose I have an API which needs to get data from two third-party APIs. So I would call this TP1, TP2. These are two APIs which I need to fire. And for some reason, so both of them probably takes an ID as an input. So there's no dependency on each other, right? So I can call these two individually. One way to do is I would make a call to TP1, get the output back, basically like a sequential thing, right? And then again call TP2 and get the output back, and then basically proceed with the further processing, right? Like I can continue doing this, right? I can do this, right? Another way to do this would be, I would have like one thread created, like I will create a thread one, and I will ask them to like process this TP1, like basically make an API call to the third party. And then I'll have another thread two call TP2, and I can basically do this at the same point of time, right? And then I would say that when both of these are finished, probably do some aggregation or the same processing and move ahead. I can do this, right? Did you guys understand this example? In this case, what happens is, okay, first of all, did you guys understand what the difference is? I'm doing a sequential call here. I'm doing a parallel call here. Okay. The difference would be, suppose if this API, if TP1 takes like 1 second, both of this like probably take 1 second to get called, right? In the first case, like get a response back basically. So the TP1 takes 1 second, and then the TP2 takes 2 seconds, 1 more second. So basically, I'm gonna take like 2+ seconds in this kind of processing, right? Most of the time. In this case, and I'm ignoring the overhead to create a thread and things like that. If you look at this, I could do this in somewhere close to 1 second. Probably to do more than 1 second because you are gonna take some time to create threads and things like that and overall. But you can see that I'm able to do the same thing in probably 1+ second. I'm saving on 1 second, right? And these kind of things are gonna be useful when we talk about the other. There's some terms like latency and throughput, but I'm gonna discuss this later. But do you guys understand this example? Why would somebody want to use a thread? This is one use case. There would be multiple other use cases, but do you understand in an application where you see something like this? Okay. Okay, got it. Yeah. So where were we? I just lost a track of it. So we're talking about processes and threads, right? So do we have a basic understanding of what a process is and what a thread is? Right. Okay. Nobody has a hands up and nobody says do 2 thumbs up. So I think I can go ahead, right? Yeah. Okay. Now, so we're talking about one particular, like a single machine, right? A single machine like a laptop, right? So even in a single machine, you have multiple CPUs or multiple cores as such, and you are able to do multiple tasks, processes, or threads and things like that, right? Okay. But think about this. Today, suppose I'm running something on my computer and I'm able to do like 10 tasks at this point of time because I had like probably a 2-core machine. Now, suppose for some reason, you can think of this like I became like a huge expert in multitasking, and now I want to do something like a 20 tasks. Right? Probably still, I don't see much visibility of latency and things like that. I'm still being able to process this in a 2-core machine. But suppose going forward, I have like 100 tasks. Now I want to do all of this in this 2-core machine. It starts becoming a problem. You would start seeing some latency. You will start seeing some applications getting stuck, some getting freezed out and things like that, right? Why? Because you're trying to do too many tasks. And sometimes the OS would do is, it feels like you're doing 100 tasks, but it will not be doing 100 tasks internally. Probably it will not tell you spawn more tasks and things like that. Or you say like resource. In Windows, we used to have in the past, like it will say that there's no resource available to do this and things like that. You start getting like this loading and things like that, right? The loader keeps on coming, right? So you can see this, that you can hit limits in a single machine, right? There are going to be some, like some number, probably these are hypothetical numbers, so the numbers might be still larger, but you're going to hit some limit at some place of time where one single machine is not able to do all the things which you want, right? Then what do you do? Then how do you get out of that situation? One way to get out of that situation is to increase the resources. So, I mean, resources in general means memory. CPU, memory is basically RAM. Think of this, right? Memory and CPU, mostly, and probably like a network bandwidth and things like that. But this is what resources in general means, right? And this is something which is this term is gonna be used extensively. But yeah, it's a generic term for all of these as such. So you can see that one way to deal with this is like increasing the resources, which would be like instead of 2-core, I go to a shop and basically tell them like, can you do something like, can you add more cores to it? Like nowadays, you can increase RAMs and you can even increase vCPUs. Not possible in Mac kind of machines. Mac machines are, I think, are quite restrictive in this, but like in Windows, you can do it into certain, right? And a lot of people do assemblies of their own, right? So you would have more slots and things like that if you can, right? So you can increase your RAM, and you can, I think in some places where you also be increase like your CPU and counts and things like that, right? So if you're able to increase all of these, right, you're gonna like you can increase the processing power or the resources for your system. And now probably instead of doing 100, you can still go and go to like 1,000, right? But one thing you should remember, that these machines, the more higher you go, the more expensive it gets, right? But this does not guarantee that you would be able to do unlimited number of tasks, right? You are still gonna hit a limit. Suppose you are trying to run your computer as a web server, and suddenly like you go viral and people start coming to your website for some reason, and now you might have like a 10 lakh people visiting your 1 million people visiting your website at the same point of time. Now your CPU, sorry, your computer might not be able to serve all of them, right? For some, there might be something which would be like overutilized, right? For example, your CPUs are not being able to serve as such, right? You cannot keep on increasing these resources for a single system. You will hit a limit, right? Because there are other components also which should be compatible with that component as such. But even if you think about this, there is going to be a time when you are going to hit the limit where you will not be able to add more resources, right? Then how would you basically go ahead and address this? Now I still have that server running. I mean, I see that there's a requirement to increase the resources because my good old computer is not able to serve this. How will we do that, right? How will we achieve where we can run more number of tasks and things like that? Any idea? How would we serve the traffic, basically, the increased traffic as such? Suppose I'm getting like a 1 million requests per second. Yeah. Okay.
Increase the servers.
Yeah. So this basically means that if one machine is not able to serve my purpose, I need to use multiple machines, right? And so what happens in this case? These are multiple machines in the background, but they're basically acting as one, right? One web server, I would say. Like, sorry, my writing is really bad, but don't mind. Yeah, so you can think of this like I can increase the number of machines, and we're going to talk about how you can build a web server where you can have multiple machines in the background. But for time being, I'll just think of this: if I hit a limit on the resources, I can add more machines, like probably have 2 machines, and you can think that half of the traffic is going to one machine, and half of the traffic is going to the other machine. How it is done, probably we can use something like a called as a load balancer, but we're not going to discuss this right now. But you think about this, it's able to achieve that, right? But for the outside world, if you look at this, both of these machines actually make up one particular server, I would say. That's basically like a web server. So it's acting as one, but inside it, it's not one, right? It's multiple things, right? So when you do something like this, right, where you have multiple machines who are like where you can use this as a one single unit, or you can share resources among them to do one kind of task or things like that. It's called as a distributed system, right? Is it clear what is a distributed system? I mean, what do you mean by distributed system?
Can you repeat the last line?
Sorry, the last one, right? Okay. So you can think of this as multiple machines are combined to do one kind of task. So you can think of something like this, right? So I have a web server. For the outside world, this is W1. This is the web server, right? But inside, I have multiple of these. I could say like I would say C1, C2. Probably I should say server 1 or server 3, server 4, right? If you look at this, W1 seems to be one, right? From the outside world, when somebody calls, like when I'm trying to use a particular database server or particular web server, right? It seems to be like one machine, right? It acts like a one machine. But if you look inside, if you go deep inside, it's not one machine. It's multiple machines who are trying to act as one. So what are you doing here? You're trying to share resources and do things like computation and other things to basically act as one unit, right? So this is one unit. I mean, if you look at this, I can just call it like, sorry, probably I will leave out the web server for me. This is one unit, right? This is acting as one unit. This is all one unit from outside. But is this one unit? No. It's different number of, I would say, computers or instances or things like that, but it's acting as one unit, right? So if I have a generic term for something like this, it is called as distributed system. Because I have distributed, like the resources are going to get shared and I have distributed it into multiple machines as such. Why I have done this will come into later, like how is it useful and things like that, right? But if you look at this, you understand that like how it works as such. Hey guys, sorry about that. Yeah. So basically a distributed system is when multiple components, or in this case, we can say like multiple computers are distributed on a network, like they are distributed on a network and these act as a single unit, right? And you can split a work between them. You can say that, okay, this will do some part of work, this will do some part of work, and you can split them in different ways, right? So one way to do this is one request will go to this particular instance. Like for example, one request goes to server one, like I would say request one goes to one, request two goes to server two, request three goes to something like this. So you're dividing it based on the request. One way would be the same request goes through multiple of these servers to do different kinds of job. For example, it goes in to do certain like task T1. The request one goes to server T1, server S1 to do a task T1, and then it goes to server 2 to do T2, some task, and then to T3, like T3 task from S3, and then it basically turns back to the, like it gives a response back. You can do things like that, right? Okay, Shivan, yeah.
So then what is the difference between these microservices and distributed?
Yeah. So, okay, we are jumping the gun, but yeah, in one way you can think about this, distributed systems is a very wide variety of like, it's the, like whenever you do something where a single unit of, like a single unit of your resource or a single computer or something like that is not able to serve that purpose, right? You would have to add more resources to it. And sometimes adding more resources just means adding more instances of that particular computer or like host or things like that, right? This is in generic called as distributed systems. Microservices is a very generic term, like it's a term used in web servers and things like that. So it's the same thing. You can treat, I would not say it's completely same. I mean, but I would say that you can use microservices as a way of saying that microservices are all supposed to be distributed systems, but probably not the other way around, right? But in a web world, whenever you try to distribute work over multiple servers and things like that, it ultimately becomes a microservice as such.
Is S1, S2, S3, S4, I can say there's a microservice which is doing different tasks and combined like on call as a distributed system.
Yeah, you can. I mean, it depends on what the use case is, right? So one way to, like in general, if I'm going to talk about, okay, so let me draw an example to show microservices. The same example, I could say that, okay, it's a web server 1, server 2, server 3, server 3, server 4, right? These four are running an application which is the same. Like for example, it's running something as a user service, and I'm having like 4 instances of user service running, and these are combined into one. And this web server has a, again, I don't want to use these terms, but yeah, because again, we'll go into discussions of load balancers probably, which you want to cover later. But you can think of this as like, this can be like a microservice running with multiple instances, right? Even in microservices, right? Microservices also are running with multiple servers or multiple computers or things like that, right? They are not going to be one instance of a micro like service running. You would run like multiple instances of that, right? They can combine to make up one particular kind of microservice, but they are also going to be distributed into multiple computers or multiple resources. Is this clear?
Yeah, clear.
Yeah. So yeah, we are going to discuss about microservices and monoliths when we get there. But yeah, for the time being, we can do this. Yeah, Sumit.
So these four machines or computers that are serving the different tasks, they belong to the same process. Do I need to think like that?
Yeah, so they would not be. So think once you talk about different systems, right? For example, server 1 and server 2, right? Like most of the time, I mean, I would just say this, like these are going to be different two processes, right? They are not going to be the same process as such. They're going to be different processes because this is running in computer 1, or this is actually computer 1 and this is computer 2, right? So you cannot run one process across two systems. The process, you would say that the boundary of a process is one system. You cannot do like beyond that. So these are two different processes running, if I would say. And this is where something we're jumping the gun, but I would talk about this. There's something called as RPC, remote procedure call, or sometimes people call it as remote process call and things like that. And there's something called as gRPC. gRPC, yeah. We're going to discuss about both of these, but for the time being, just understand this, that if you're talking about server 1, server 2, and these are two different computers altogether, they're going to have different processes. They will not have same process as such. The process boundary is one particular computer, I would say, or one particular things like that, right? So outside that, it's going to be like a different process altogether. Okay. Is this clear to you guys? Do you guys understand a basic understanding of like what distributed system is? Okay, I saw multiple thumbs up, so I will go ahead. Okay. So there's a basic definition of distributed systems, which I already talked about. There's a basic diagram which says like this is one application running multiple nodes, and multiple nodes can be multiple instances. So these terms like nodes, instances, and hosts are generally used interchangeably. Don't worry about it. Most of the time they would mean the same, so it's fine. Okay. Now, because I think you guys have some understanding about distributed systems, right? I would want to know why would somebody want to use a distributed system, right? How does it help? I see that at a certain point of time you're gonna hit some resource limit. It means that you're not able to do like more amount of work with one particular unit. You can treat this unit as one computer as such, but you're gonna hit one like a limit. So what you need to do is you need to add multiple more of these, and which basically means that you are gonna able to serve like more. You will be able to do more of these kind of work, right? So that we can treat as scalability, right? So when you're able to do something like more amount of work, you can think like you can scale. And this is the term which people use quite often, right? So can you scale this up to 1,000 users? Which basically means that if one particular instance or one particular node is able to do like handle 100 users, now if you want to serve 1,000 users at the same point of time, you would basically have to add like 10 instances for this to scale up. While adding those, like when you try to scale up, what you need to do to scale up, right? You need to add some things like request forwarding using a load balancer and things like that, right? So this is the term scalability, which basically means that you are trying to do more amount of work, or you're trying to scale to do serve more requests in a normal world or in a client server model. It's basically like you're trying to serve more requests. In other words, it might mean different, right? So for example, if you are running cron jobs and things like that, it might mean a bit more different, right? You could say something like, I want to serve 300 GB per second and things like that. If you're trying to do streaming and things like that, it's not only the number of requests that counts there, it's also like the data which is getting transferred on the wire and things like that. But in general, scalability basically means that you're trying to do more unit of work, or the work might vary as such. Yeah, sure.
I wanted to say that scalability does mean that the system should like as the load increases, the system like should be able to handle that load, and also we need to take care that the response time also is not affected. Because if main motto is to serve load, keeping the response time same.
Yeah, so you're right. I've talked about this in the throughput and latency and throughput slide. I don't know where it is. Sorry, this is different. This is different. This is different. I have somewhere efficiency. Yeah, I think this is a waste. Right? Sorry, this is not the place. Yeah, this is the one. Sure. Which really says you should aim for maximal throughput with acceptable latency. This is the mantra I would basically say. But yeah, we'll come to this. We'll come to this later. Yeah, but you're right. That is what scalability is. Basically, you're trying to do more amount of work. But when you're trying to do more amount of work, you should also think about that. You should not be like, it should not be like, okay, so today you're doing 1,000 units of work, and it was taking some X amount of time to do 1 unit of work. But tomorrow, when you're doing 10,000 units of work, it's taking you X into 100 amount of time to do that work. That basically does not mean that you are able to scale the system, right? Okay, there's some basic information in the slide. I think you guys can go through it. I'm not gonna read about this because it basically means that the same thing which you discussed. Yeah, so this is something which I liked about this. These two lines, basically performance versus scalability, right? So, and I don't know whether you guys, anybody of you has a background in performance testing and things like that, but for them, it would be like they would have come across this term as performance, right? So you can just read the next two lines and you'll basically be able to get this. If you have a performance issue, the system is going to be slow for a single user. Like even one user, so you can think of this, like for one user serving that request, one request would take like 5 seconds. Right? And 5 seconds is really bad in software world. If for a single user, only one user is processing only one user is processing at this point of time. But even then, if it takes you 5 seconds, then you have a performance problem. But the other scenario would be if only one user is there and you're able to serve that in 1 second. 1 second is even bad, but let's assume 1 second is better than 5 seconds. If one user is there and you're able to serve that user in 1 second, but if you increase the number of users, for example, if I have 1,000 users, and then what happens is if I'm trying to serve 1,000 of these, each of these like takes 5 seconds. That it means that I have a scalability problem. So you see the difference, right? So even if my system is slow for one user, it basically means that there's a performance issue. But if for one user my system works fast enough, but for more, when I increase the number of users, it starts like increasing the latency is that word. But if it starts taking more time, it basically means I have a scale issue or a scalability problem. Yeah, you guys understand this? Because this is something where a lot of times while answering these questions, if you understand this properly, right, you can use these words better, and probably it's a good impression on the interview as such. So performance basically means even for a single user, if you're having issues, then you have a performance issue. But for one single user, if it works fine, but when you increase the number of users, it's not working fine, then you have a scale issue. Simple as that, right? Okay. Yeah. So now coming to this term called as horizontal scaling and vertical scaling, right? I think we have already discussed this, but for sake of discussion, so remember an example, right? When you were trying to increase the resources of one system. So I'm just trying to add more CPU or add more RAM to this. It means you're scaling it vertically. I'm adding more resources to it. Probably, I think I have a diagram. Yeah. So if you look at the left hand side, right, the vertical scaling basically means add a like small server and add more resources to it. It became a bit bigger, and then added more resources to it, becomes like more bigger as such, right? On the right hand side, horizontal scaling means I had one instance, I increased the instance to 2. I felt that it's still not able to scale up to the request which I want to, or scale up to the number. I'll add more instances and I'll keep on going. Yeah, Sumit.
So adding more resources to the same server, I think of CPU and RAM, right?
Yeah. So adding more resources basically means adding more CPU, RAM, or increasing the network card, adding multiple network cards and things like that. But horizontal scaling basically means adding new instances of the same type, right? So you can add 2 more instances, 3 more instances, and 4 more instances as such for the same thing. Okay, is that clear? Okay. Yeah, and so what happens, like if you look at it in terms of this, right? Once we start doing distributed systems, when we start adding more resources, it's, I mean, somehow we end up like making the servers more reliable. So I'm gonna stop this sharing. I'm gonna go back to the sharing my iPad. Yeah. Can you see my iPad screen? Okay, now I think you can, right? Can you see the screen? Yeah. Okay. So think about this, right? So I'll take an example. I have a web server, and I'm calling it web server, right? And I have like multiple instances of servers. I'll say S1, S2, S3, and S4, right? In this setup, even if for at certain point of time, right? And one more thing which I would want to say that at any like never assume that in a software world everything is reliable and everything is going to work as it is, right? They're always going to be failures. They're going to be network failures, which is really going to be high, and we're going to discuss this in the cap theorem. You can never assume that your network is going to work forever, or it's going to work like in 100% of times. You are always going to have issues with network. The same thing goes with hardware and software also, right? Anything can fail at any point of time. Your hardware can get heated up and it can just run on, it can burn out and things like that, right? So what generally people tend to do is people tend to account for these failures. So saying that at any point of time, even if there's some failure, they can be failures which are like failures for all, right? Like even if you have redundancy, in this case, if you look at this server 1 to server 3, 4, assuming that this is doing the same kind of work, even if one of these goes down, right, I'm still having these three to basically be working properly, right? So these three are able to serve requests. So my system is still be like, I'm still able to do some job, right? There might be issues. I mean, there might be like scaling issues if you only have 3 servers instead of 4, but you're still able to process something, right? It's not 100% downtime, or I would say in that sense, right? So if you look at this setup, right, this makes it more reliable. This is more reliable, right? Can you see this? This setup makes it more reliable because I have 4 of these working, and like there might be failures. There might be failures, there can be chances that all of 4 of them, like for some reason, fail at the same point of time. There are failures like that also. You might have a software problem where you have written something and like it fails all 4 of the times. But in general, I could say like if there is some other failure, like a hardware failure or things like that, 1 or 2 of them will go down, but still I would have a few of them working, right? So it's better than having one instance as such, right? So this is going to be more reliable.
Is this what we call that fault tolerant?
Yeah. So fault tolerance, I mean, reliable basically means if a system is more reliable, it basically means that it's more fault tolerant as such. Yeah. There are other things also which when you do fault tolerant, I would say there are different levels at which you can do. But yeah, one way to do fault, like one way to say like increasing your fault tolerance is by having a distributed system as such. But there are other things which you can also do, right? In fault tolerance, people do a different they could have like backup servers and a lot of different things people do to like increase, like basically take care of fault tolerance as such. But one way to do this would be adding more servers or having a distributed system as such, right? Suppose I have another web server 1 where it was like I try to do vertical scaling. So basically I have one instance which is like kind of it might have like a 64 code, right? But this is one instance as such, right? This can go down, and when this goes down, this server is also down, right? Because nothing works anymore, right? For in this case, right? So this is not reliable, I would say. Is it clear? Okay. Now availability also, I mean, reliability and availability are like terms basically more or less are quite similar, I would say. But basically try to understand this is the same thing, right? If something is more reliable, it means it's more available. But vice versa can be a bit different. But yeah, so I could say that like my server is more available in this case, right, compared to this. Because in this case, if one of the instances goes down, everything goes down. Whereas in this case, even if 2 of these goes down, probably I have to. and there are different ways I can do all of these. Like I could take care of these failure scenarios, but yeah, in this case, I have more reliable and available system as compared to this case. Right? Wait. I would move on the slide. Right. So now coming to efficiency, which is the things which people are talking about, right? Okay. So again, a setup, right, where I have a server or a web server, and okay, no, in this case, probably I should take a different example. So suppose I have a web server in the middle, and I don't need to specify so this is a distributed web server for a timing. We just assume this to be a distributed web server, and I could have like, so these are the clients, and assume this to be a mobile app. So this is mobile app 1, mobile app 2, mobile app 3, and then they can be multiple, right? So mobile app 4 and so on, right? And I have a web server here, right? So the way we measure efficiency of a system is by like two things we need to take care of, right? Or two things in which you can say your system is more efficient as such. One is called as latency, right? And the second is called as throughput. Okay, and you can think of this, one simple way of thinking of this is latency. And generally, when people talk about latency, you would have heard things like, right, the user API takes 100 milliseconds to process like one request, or has an average P99 as average response time as like average response time, which is like P99 as 100 milliseconds. Have you heard these kinds of discussions in your orgs or anywhere else? Like people talk about saying that this API on like takes on average like 100 milliseconds. Anybody of you have heard things like this? Understand these kinds of terms? Okay, seriously, nobody?
No, while using the cloud, they will mention.
Yeah, I see like Charanjit Singh just having it. Yeah. So, okay, I think then probably we should talk about this. So, latency and response time, right? Suppose I have a client, I would say C1. It makes a request to a server, this one, and this is a request, and this is a response, right? And if you measure this request and response cycle, so this is in generally a client server model, this is how it works, right? So this is true for a client server model. There are other models also, probably for the sake of simplicity, we'll just discuss this client server model. When you fire a request from a client to a server, the server will do some kind of processing, and then it would give you a response back, right? So this one cycle, a request response cycle. So this is a request response cycle, I would say. Right? So request response cycle, you measure this one request response cycle in terms of time taken. So I could say that in order to serve this one request or the one response, generally in order to serve one request basically means that you get the response back on the client side itself. Right? It took me 100 milliseconds to serve this request. Right? What this basically means is if I fire a request from this client, it goes to the server and then it comes back. There are different places in which, with respect to where you can measure the time taken, you can look at, somebody can want to measure it with respect to the server, saying that from the time I got a request on the server to when I send a response back. If I just want to measure this, because I don't want to take into account what was the network conditions for the client, I would just want to measure it in this space, right? Because somebody working on somebody had a 2G mobile or like a 2G network as such, they would take more time to get a response back, whereas somebody on a 5G would get it like earlier, right? Because the network is faster and things like that, right? So suppose somebody or my manager in this case, or somebody from a team comes out and says like, I want to know what is the latency for our users API. Suppose this is a user system, right? Users API, right? So what you can do is you can basically look at the time taken for like each request. When does the request comes in? Let's suppose the request comes in at T1 and you give a response out from a server at T2. If you basically do this T2 minus T1, you will get the response time or the latency, right? Which basically means that this is the time taken for a server to process this request as such. And we don't do it for individual one. I would say you will never do it for one request. What you do is you do it for a lot of times, right? So for example, one request would have like, so suppose I do this T2 minus T1 equal to R1. I would have like 1,000 of these kinds of requests, right? So what I do is I add all of these responses times back and divide it by the number of requests, probably 1,000 or something like this. And then I come up with like some average, right? So I say like average is 100 milliseconds, which basically means in most of our cases, we are giving a response back to the user in 100 milliseconds. And like we use the terms latency and response time interchangeably as such. Do you guys understand this? Okay, I got 3, 4. I'm assuming this is the majority. So yeah. So this is what it means by response time as such. And next time, if anybody comes back to you and asks like, what is the latency of users API? Or somebody can ask you what latency of the system itself. Generally, latency of systems are not a very right pointer, because there might be 10 different work which your system might be doing. And it's very hard to basically understand why the latency would be high in that case. So in general, people would go to an individual level and say like, okay, can you tell me that users API or that individual get users API or get our individual user or get user based on ID, right? API. What's the latency for that? And you say like 150 milliseconds. Somebody can come back and say it seems to be too high. How can we improve that? We'll discuss about those kinds of things also in the future classes. But for our timing, just understand this, that what does response time actually mean? Yeah, sure.
Here, T1 is request time and T2 is response time, or like?
Yeah. So if you think, so when I'm talking, as I told you, right, you can measure it in respect to the client. The problem with the client is in between this, right? This is the network, right? And I'm not really sure about how the network is. Network is on this side, right? Somebody might be on a very slow network, right? Generally, what we do is we don't use this as a marker, and this is something called as perceived latency, which is basically how the user sees the latency as. But because we are not going to be very we are not able to make sure what kind of network it is, right? We generally stay away from that kind of a thing until it's required. The other way to measure this is in terms of with respect to server, right? We are going to measure like what is the time taken to process the request. So suppose at time T1 I get a request, and at time T2 I give a response back for the same request. So I want to do is T2 minus T1 as such. That would be my processing time for that request, right? Okay, yeah. Okay, so I would also want to talk about something which is going to be useful, but you would hear terms like this, and you should use terms like this. There's something called as P99 and P95, right? Which is basically like 99 percentile and and 95 percentile. What does this mean? It means basically that what is the time taken by the API 99% of the times? Because systems tends to have this behavior in which at some point of time you would like see a spike for one of the requests, right? So out of 100, you would have like a spike in one request. So if you have 100 requests, right? For example, you can assume like if you're having 100 requests, right? 99 of these would be served in 100 milliseconds. And for some reason, one request would basically take like a 500 milliseconds. Why? There might be n number of conditions which can happen, right? You can think one of the things might be that OS was doing something, some operation or some maintenance at that point of time. Maintenance in the sense like it could do certain kind of different tasks at that point of time, and it was like, okay, I need to do that. That is a higher priority for the OS than compared to serving a request for some reason. there might be a case, right? So you might see a spike, right? So this is the reason why people depend on 95 and 99 percentiles, which basically means that out of like 195% of the times, right, it was taking 100 milliseconds. So you can assume that this is okay. 5% of the times, or in some cases in P99, 1% of the times, you might see a abnormal behavior, but that's fine. That's expected because systems would not be consistent always. There might be things which going on in the background, right? For example, if you're working with JVM kind of a thing, there might be some cleanup happening, right? The JVM might be running a cleanup and things like that. So it might do a, like there, okay, not going into Java details, but it might pause what things it was doing to just do the cleanup first and then serve that request. In that case, you would see a high latency, right, for that particular request. So nothing to worry about. This will happen. This will happen for different reasons. That's the reason people use P99 and P95 to measure these kinds of latency and response time, and not average as such. Okay, but yeah, you can talk about this. You can even tell it as average, but when we use terms like P99 and P95, people understand that what you're talking about, and it's more accurate, I would say. So we've discussed about latency, and which we can say that time taken to serve one request, right? Like serve 1 unit of request, 1 unit request, I would say. Shit, I'm missing something. Right? Throughput. So you can, okay, now before coming to throughput, right? Have you heard things like this user's API has a throughput of 100 requests per second? Has anybody come up with things like this, right? In the web world, it's very common when people talking about scalability, performance, and things like that, and they say like excuse me, somebody comes back to say like, we're able to serve 100 requests per second. What does this basically mean? Have you heard all of this? Like, okay, I saw one thumbs up. I don't know what the others. Okay. What basically it means is, like, going back to the same example, right? I was able to serve one request in 100 milliseconds, which was basically a measure of one request. In this case, one request. In this case, I'm doing is the other way around, right? What I'm trying to find out is, in 1 unit of time, how many operations I'm able to do, or how much work I'm able to do. Check. Right. So if you look at this example, it basically means that I'm able to do 100 requests per second. I mean, 100 of these users API calls are supported by our server in this case, in 1 second. Okay, I'll take a pause. Did you guys get this? I see Anil having a thumbs up. I see Chandana having a thumbs up. Okay. Yeah, anybody has any doubts understanding what? So there are 2 ways in which you can measure efficiency of a system. Ashraf, I'll come back to you, just give me a moment. In 2 ways you can do it, right? One is, what is the time taken by one request? The other would be, how many requests can I do in a certain interval of time? So it can differ, right? It can be in seconds, it can be minutes, it can be in hours also. But this is, I mean, combining both of these, I'm able to come up with a number where you can say that, okay, how do you measure the efficiency of a system? You measure it by throughput and latency. Latency is basically one request, how much time it takes, or average cases, or P99, P95 cases, what is the time taken by the request? And the other one is, in this amount of time, how many unit of work I'm able to do? And the unit of work can differ, right? So, yeah. Okay, I don't see that hands up anymore, but yeah, Ashraf, and I think Uzeen, you guys had a question.
Yeah, I think I'm fine. I'm clear now. Yeah.
Okay, yeah. Okay, Uzeen, do you have any questions?
No, I also wanted to ask that it will be always per second or anytime.
No,
So
no.
you already answered.
Yeah. So, I mean, basically, that's the reason I said like unit of work, right? Unit of time, right? So it can be any unit of time. So In some cases, in a web server world, it makes sense to do it in seconds because human brain, and think about this, right? A lot of these things like throughput and latency is for people who are related to these kinds of servers are able to understand this, right? So when I go to my manager or my director or somebody in the top, right, and we say like, okay, we are able to serve 1,000 requests per second, they would understand, okay, so 1,000 users can access this API at the same point in time. It becomes very clear to them, right? Otherwise, it's going to be difficult to have a conversation, right? So this is the reason I would say, like, use these terms. These are good terms. If you understand this, like, completely, you would have a good time in an interview while talking about all of this, right? And people expect you to talk about this. You can talk about latency. You can say that I expect the P99 to be something close to 150 milliseconds. If I want to reduce it, I can use XYZ things. I can use something like a cache. I'm not going to talk about cache in this class, but yeah, you can say something like this, right? Now it's very easy for the interviewer also to understand, okay, so this guy understands about latency, and you can say like throughput also, and you can talk about these things, and you can basically have a better conversation in this regards, right? You can still talk about like, okay, the time taken to serve a request would be this much and things like that, but if you use these terms, probably it's more impressionable. Okay, I'm looking at the clock. It's 11:25. I wanted to cover cap theorem, but I see that there's less time to cover cap theorem. Okay, I don't know what to do, but yeah. Okay, let me look at the slides. Do you have something else? Okay, I'll probably want to share some slides also. Something in the slides which will make it more clear. 1 second. I'm going to share my screen. Yeah. So can you guys see this? Like, and this diagram I picked up in terms of like data as such. This is not in terms of number of requests. Yeah, Anil, you had a question.
I wanted to know that I have one question. It's not needed that you answer here, but just I want to know that this will be covered in later sessions. So like generally we say these many like thousands of requests are served by a particular server in per second, like 1,000 requests per second. So, but if I see like YouTube, Amazon, they might be getting like millions of requests per second, right? So how those requests are served? So that's what I want to know.
Yeah. So probably you're right. Probably we'll get a better answer of this in the future classes. But
yes, that will be better. Okay, no problem. But just I want to know if we will get.
Anil, just to like serve your curiosity right here. Think about this: that if one unit is able to do 1,000 like requests per second, if you have 10 of these, probably you're doing 10,000. And if you have 100 of these, you're probably doing it. That's not true. I would say there are going to be bottlenecks, which you're going to talk about. I mean, like if your API, if that individual API or that particular like unit of work needs a database call, then can it do 10,000 requests per second? If not, then this database is going to be a bottleneck. Then how do you do it and things like that, right? So there are going to be different ways in which you'll be able to do that. But one way I would say is to increase the number of resources. Does not work for all the cases, but yeah, in some way you would have to think about this is whenever somebody tells you that from 1,000 requests per second you need to do 1,000,000 requests per second, it basically means you'll have to add more resources, right? I mean, there's no way, there's no other way. You'll have to add more resources, and you'll have to make if you have to look into the other places, right? So if I'm adding 1,000 servers now, all of these 1,000 servers are going to try to make connections to my DB. Now, will the database become a bottleneck? Most probably yes. Then how would you solve that and things like that? So that's how these kinds of communications or these kinds of things would go. Like these kinds of interviews will go. But you're right, you would be able to serve 1 million. And there are a lot of I would say applications right now, even YouTube or Amazon and like Uber and things like that, who are serving like 1,000 requests per second and things like that. 1,000 millions, I would say, some even do millions, right? If you look at WhatsApp, right? I don't know how much it does, like I'm assuming that it's going to be in some millions because everybody of us uses it, right? And it has a very low latency rate. Okay, now, if you have guys use, I think everybody of us uses WhatsApp, right? So you send this, right? The moment you send a message, you get like send instantly, right? So the latency is very low for WhatsApp. What happens in the background probably we'll discuss in one of the use case studies or in the case studies. But yeah, you know this, the latency is really low. And the latency is low for WhatsApp because you're able to send messages and it gets sent in like milliseconds. And the other thing is, if you think about this, a lot of people would be using WhatsApp at the same point of time and trying to send that message, right? Like you and me would be having a conversation. Somebody else would be having, like, I'm assuming like thousands and millions of people at the same point of time would be having that same thing, right? Sending messages. So the throughput is also high for WhatsApp. So this is how you understand this. So the latency is low because I'm getting a response back in milliseconds, and I can see that my message is synced to the server and things like that, right? You have a blue tick or you have like different types of ticks. And then at the same point of time, you can imagine that a lot of different people are going to be using the same system, right? So the throughput is also high. So yeah. And if you look at the diagram, okay, sorry, first of all, Anil, does it answer your question in some way? I understand that this does not completely answer your question, but you get that? Okay. If you look at the diagram in the slide, right, it basically, this example I picked up from like a networking world. So you might feel this is a bit different. It's not a web server kind of example, but you can see that, right? So it basically talks about time needed for one packet transfer is latency, which is basically like, what's the time taken to serve one request as such. You can assume this to be request. And the second one is quality of data can be sent and received within 1 unit of time, which is basically like how many requests can you serve in 1 unit of time, which can be a second as such. So yeah, I hope this makes it more clear. Okay. Latency is time driven. Okay, talk about this. Yeah, the other property of a distributed system is serviceability and manageability, right? I'm not going to talk about the slide and things like that, but in general, even if you think it individually, right, you can think about this, right? If I have multiple instances running, I could take a few of those down and I can do repair work on this, and still the server or the application which is there is still working. Might not be working at its 100% capacity, but it's still working, right? So I'm able to do a lot of these kinds of things, right? But in the other instance, right, when we have like 1 unit of computer or something like that, right? In that case, I have a problem. If I need to do any kind of repair and things like that, I would have a downtime, right? So I'll have to bring that server down and things like that. And then the web server would not be useful as such, right? So this is where we need to understand this also, is like, if you're using a distributed system, you tend to be saved on a lot of these things as such. Okay, now because I feel I think cap theorem probably we should cover in the next class, probably tomorrow, along with the LLD thing, because I think 30 minutes is going to be less, and I know that's an important piece where a lot of questions is going to come on. So I'm not going to go ahead and do that today. One thing which I want to ask you guys, and this is something which I'm hoping that you guys know a bit about. Has anybody worked in a distributed system setup and tried to do a deployment? How do you deploy actually? And there are different ways in which people deploy the new code, right? So, okay, now I think it's time for me to do a screen share so that I can explain you a few things. But yeah, anybody who wants to answer this, or it's okay, even if you don't know this or you've not done this, I'm fine with this. The only thing which I want to know is, do you have an idea, or can you guess how it's going to be done, right? So take an example, right? Today I have one web server, and let's take an example. I have a web server, not one web server. I basically have an application like Ola, right? For time being, let's not go into microservices and things like that. Assume that it's one service serving the whole thing, which has multiple, like one web server. Sorry, 1 second. So I have one web server, and this web server has multiple instances. I will call it as server 1, server 2, server 3, and server n, right? Now, suppose I want to make some changes. I've done some code changes. I've added some functionality. Now I want to deploy new code. Have you guys been a part of that process? And if yes, I would want to know how does this work for your org and things like that. there are multiple ways in which you can do it. So just looking for some pointers here. Nobody has been a part of like web deployments. Okay, I see 2 participants raised hand. Okay, I will give chance to Venkatesh, then probably to see. Yeah, Venkatesh.
Yeah, we usually for Jenkins DevOps.
You use Jenkins to basically deployment, right? But what is the strategy behind it, right? So, okay, I'll explain what do you mean by strategy. Do you like how do you deploy? Do you basically deploy like do you have a downtime in which for you basically say that okay you haven't you in the application it would say something like we are doing some maintenance and something like this and you just generally find this in bank kind of applications, right? Like they will always send you messages saying that in the night around 3 a.m. or 2 to 4 a.m. we are doing your app would not be like it will not be working because we're doing some kind of maintenance and it will get back like the service is expected to be normal after like 5 a.m. or something like this. Have you seen these kind of messages?
Yeah, so normally we don't inform to that user we have a downtime. We currently use that blue-green deployment, so that blue will be the old one. They serve the request. Once 100% completed for that new application, then we'll migrate that green could be serving this user request.
Okay. So I'll probably discuss about this for timing. I understand this that you guys do blue-green deployment. Okay. One would be downtime. So basically, you take down all your applications. Nothing is working at that point of time, and then you basically go into the deployment. So I'm gonna go to Uzeen for his inputs here.
So we are using Kubernetes here. So suppose five pods are running for Kubernetes. So what we are doing, we are creating a Docker image with our build, and by creating the Docker image, we are initiating one of the container. Now one container with the new build is running and 5 container with the old build is running. Then what will happen? The Kubernetes will increase one container and decrease the old container. One by one, it will increase one container, new container. And what will happen in last 5 new container are running and 1 old container is running, and at certain time of time okay, this is blue green.
Yeah, this is blue green basically in some sense.
Okay.
Yeah, but we are using containers instead of tag machines and things like that. But yeah, I mean the idea remains the same. Basically you do some deployment and then do it. Okay, Shivan, I'll go with you next.
Yeah, it's the same like we are using Kubernetes as well for the deployment.
Okay. Okay, I have Venkatesh. I think I've Uzeen. I've gone to Shivan. Okay, is there any more raised hands? Uzeen, do you want to talk about something else?
Yeah, so like in AWS EC2 instances, if we are deploying, then auto scaling group can also work here. Like we can initiate one instance and then auto scaling will change that.
So this is the same thing, right? So I mean, when you use Kate or like Kubernetes or you use containers or you deploy on an EC2 instance, the idea remains the same thing, right? What you're doing is, suppose there are n number of instances at the server. What you're doing is you're deploying 2 instances with the new build, and what you want to do is you want to test first that the new build is working properly, and once you are like sure of this, what you start doing is you start deploying more instances of this new build, and slowly you want to remove the old instances from the traffic, which is basically using a load balancer. Again, I don't want to talk about load balancer now, but yeah, this is how it works, right? So no matter if you're using Kubernetes or using ECS, Elastic Containers, Elastic Container Service, and EC2, you can all do all of those things. The idea remains the same. It's basically like a blue-green deployment, candy deployments. There are a lot of different names to it. The funda remains the same. Okay. Yeah. I am interested in this. Nobody does a downtime deployment anymore. Like I see like 12 people, like 11 people, 12 people, including me in the call. Like nobody does a downtown deployment anymore. Like nobody works for some bank or something like this where we'll say like, okay, we're not going to take any risk and all, and we're going to bring everything down, or there's no other way we can do it, and we'll have to get a downtime. Okay.
Previously, I did that as it. Like previously, when I was in banking project,
yeah,
I had done that. We had kept some downtime page, and we'll deploy all the new jar in all the instances of the downtime.
Okay. Got it. Yeah. So Soumya, you go ahead.
Yeah, we do the same thing. We go for a downtime.
Yeah.
So when it is a non-peak time, the downtime time remains at that time, and we deploy to all the data centers at a time.
Okay, got it. So Soumya, interested, is this like a banking or a fintech kind of a thing?
Yes, banking application. And like in our project, we don't really go for the blue-green deployment because it gets a little complex.
Yeah, I get the point. And a lot of times, right, it is what it is, to be honest. So I know why the reasons why would somebody from a banking world would do this. Probably we're going to discuss this in the future. We're going to talk about what are transactions, why do you need transaction systems, what happens in a transactional system and things like that. When you try to do a deployment, when you try to add indexes and things like that, you probably would want to stop the systems rather than so think about this also, right? Okay, now coming to a different part, right? I'm discussing something which I probably want to do in some times later, but okay, Uzeen, you have something.
Oh, what is the demerits of having blue-green deployment in fintech or banking domain?
Yeah, so I would not say there's a demerit, but you can think about this, the reliability at that point of time is very less, right? So suppose, think of this. In running systems, when you try to do some changes, right? Some kind of changes, like for example, most of these banking applications would use some kind of SQL. Why would they use SQL? Because they would want to have a transactions kind of a system, right? So if anybody remembers SQL acid, right? So this is the consistency thing, right? And this is again the same.
Maybe I can talk about a very specific problem that we face in our project. So what happens is, while doing a transaction, we usually store all the data in the database for 1 week time. Now, any change in the feature changes the database structure as well. So if we go for the blue-green deployment, the problem, and we have only one database server. We do not have multiple database servers. So what happens is, if we have one field of not null or any constraints we add, then blue-green deployment will really not work for us, because the new application, I mean, see, we'll have the old application instance and the new application instance, right? So the database is already changed. So somewhere something will fail.
Yeah.
So that's the reason we go for a downtime.
Yeah. So just in case if you guys were not able to follow, I'll just follow this up, right? So think about this. Okay, first of all,
hello, am I audible?
Yeah, Soumya, you are audible. Can you hear me, Soumya? Hello. Okay. So were you guys able to like hear Soumya? I think I was, at least.
Yeah, we are able to hear both of you.
Okay. Yeah. So I think she's having some problems. Okay. So I wanted to ask her a question, that why do you have only one instance of database, and like one database, I would say not one instance, but one database as such, or things like that. But I think...
my internet went down. Sorry.
Yeah. So Soumya, again, this is a question to you, right? So you said like you have one database as such, right? Why do you have one database?
So it's not a very big application like Amazon or something small. So we don't need really the databases in all the regions.
Yeah. But okay.
I mean, the application architecture is such that we have only one database server. So this problem is very specific to our application, that blue-green deployment will fail.
Yeah. So and I would say that because you're storing transactional kinds of information, right? You probably want to have consistency, right? So it should not happen like at any point of time, right? If so, think of this, right? I'm working in a banking domain. I'm trying to build like some systems where it like I'm keeping a track of deposits and like whatever withdrawals I'm doing, right? So if, and probably we need to discuss this in the cap theorem itself, but yeah, if at some point of time, right, I like I've deposited some money, I would want, like, you would want that to be consistent, right? So I've deposited that money into the bank, right? Now, it should not happen that if I make a request at like even after 1 second or something like this, right? It should give me the right amount that happened, right? It should not show me the previous amount. So it should show me the exact amount at that point of time, right? It should be consistent. So at time T1, if I deposit like 100 rupees, at time T1 delta, I should get that amount, right? It should not happen that I should get the previous amount without the new deposit which I've done. And in most of these systems, right, when you have multi-regionals and you have like these NoSQL databases, what happens is they have a concept called as eventual consistency, which basically means that at this point of time, you until unless the same data gets written or replicated across all systems, you would not get that same response. So it might happen
Right.
if I have like 3 instances, right? If I probably have 3 instances of a database, like the first instance wrote that particular deposit thing, and it has the right amount. The second and the third, so what happens is internally is trying to replicate those to the other databases, right? But because I made the request at the same point in time, and I'm not sure which server the request is going to go to, it might go to the second database or the third database, right? What happens is if it goes to second database and this write has not been completed, it will see the old amount. Now it's a problem, right? Somebody would panic, like, where did the money go? And did it get lost and things like that, right? I'm just giving a very high level thing. Probably there's a lot of other things or other use cases also which might fail, but you think about this, right? This is an eventual consistency thing, right? Which is going to kick in, which is good. Eventual consistency is not a bad thing, but for some use cases, it might not work out. And this is one of those use cases, right? When you have a transaction-based system, you would probably don't want to do that, right? Asha, just give me a moment, I'll come back to you. So in this case, probably what you want to do is you would want to not use a transaction, like you would want to use a transaction-based system, and something like a SQL works well for it. There are other reasons also. There is something called as transactions, and this is not the transaction of money. This is called as database transactions, which you would want to have, which is supported in SQL, which is not supported greatly by all of these NoSQLs, and there are reasons for it, right? So the reason would be mostly consistency, which means that after a certain piece of data is written into one of these databases, it should always give me the most recent update on the database itself. It should not give me the previous thing, which might happen in case of NoSQLs, right? And coming back to the deployment part, right? The reason why this would not work is in most of the SQL systems, you would want, like, one of the primary requirements is the structuring of things, right? The structure, which you can think about as tables and as columns, tables and columns, right? So at any point of time, if you change a constraint, right? For example, as you said, right, not null and versus nullable, or previously it was not null, or if you make it more expansive, right? It was not null before, and you're trying to make it null, it's probably gonna work. But if it's the other way around, where it was a null before and you're trying to make a not null constraint now, or modify a not null constraint of a database now, it will not work with that point of time, right? Because you cannot have two systems or two. So right now your applications have two different versions, right? One is expecting it to have like not null constraint. The other is expecting it to having like a null constraint. You can write code where it can work, but it becomes very difficult. It becomes quite complex going forward, right? And those, like, even if you have to write those kinds of code, right, because you have to write it, and like those are only for at that specific point of time when you're trying to do the deployment, right? People feel that instead of introducing that complexity, why not just take a downtime, have all the databases like in order, and then do it, which is a much safer approach, and which works for banks, right? Because banks are dealing with money, and nobody wants to lose money as such, right? So like one of the use cases might be this. You can still, I've seen people using SQL where they're able to do all of these things safely in some sense, where they have like written a code which is like when you say like it's backward compatible code. So it's backward compatible to the code which is before. You write some application logic there and you'll be able to do that. But it gets very difficult, I would say. And sometimes it's just not possible to do that. And then probably you want to do that. Even adding indexes. So a lot of times these SQL systems, right, when you try to do things like adding indexes to a very large table, right, a table which has like million records, and now you're trying to add an index. What happens is, I mean, generally the behavior at that point of time when the index is running or when the index creation is running, right, because the database server is going to take a lot of resources to do that. At that point of time, the latency would increase or the throughput would reduce and things like that, right? So sometimes people just want to make it more simpler and safer. So that's the reason they want to do that. Right? So this is the reason why would somebody want to take a time. Right? There's a bad thing, no. Probably we would want to avoid that because most of the time, right now, people say that okay, my uptime of the application was 100% or 99.999%. This basically means you don't take a downtime and things like that. So yeah. Okay, Ashraf.
I got some to some extent, but like I was not able to understand like how blue-green deployment will affect strong, consistent systems like transaction systems.
Yeah, think about this, right? So you have to, like, you have at the same point of time, you have one database which will have only one structure, right? I mean, either you have a not null constraint or you have a null constraint, right? I mean, I'm just taking an example, not null or null constraint. Right? But you have like you have two versions of the like the code running. One expects it to be not null, the other expects it to be null. Now, based on if the request goes to the old server and you have already applied the new changes, database changes, right? It might not work, depending on what the changes are. But you can think of this, right? It might not work for the, like if the request goes to the old server, it might not work. If it goes to a new server, because the new server is compatible with the new DB changes, it will work. Is it clear?
Yes.
I mean, there are multiple examples in which it's gonna like pan out in that sense, right? So think of this, the not null constraint, or like there can be a lot of other things also, right? And as she said, right?
A new sequence and using that sequence in the code. So in the new deployment, I mean, if the sequence is not there.
Yeah. You can also think of this like you also sometimes need to create a lot of things on the database based on what new features you want to add, right? So once you like if you're using a new table, probably it's fine because the old code does not know about this new table and does not use this new table, so it's fine. But at a few instances, when you're trying to modify a table, for example, you're adding a few columns or you're modifying a constraint, right? Modifying a constraint is I would say, is one of the primary use cases which might come, right? So tomorrow you had some other constraint. You basically allowed somebody to add null values. Now today you don't want to have this null value. How would you deal with this? Okay, yeah, sure.
Yeah, same. I think I forgot to lower my hand. Yeah.
Okay, fine. Yeah, but you get the point, right? I'm saying we can discuss about the instances where it will not work, but we can always think about things where it will not work, right? Because NoSQL databases are very flexible in terms of their schemas, right? They are not having a very hard, like, okay. So some people also, something before I forget, right? Once again. So when SQL and NoSQL, I'm not going to discuss all the things, but something which came top of my mind is this, right? SQL, when you're writing, you check the schema. On write, basically it checks schema. Right? So when you're writing something, it basically will check the schema and constraint, right? So when you say like this is supposed to be not null, then it is supposed to be not null, things like that, right? NoSQL, it's basically on read. When you're reading, it's not schemaless. A lot of time people say that NoSQL is schemaless, which is not true for most of the cases, right? What basically it means is on read, you will have to basically when you read something from a database, you'll have to put it into a structure, right? That structure might be a JSON structure, but it's a structure, right? A JSON or something like this, right? A lot of people say MongoDB is the best, and I know a lot of people who would say like I would use JavaScript and MongoDB and everything works fine. Probably works well when you start off the applications, but will not work when after 2 years or 3 years down the line. It might get like horrible for you guys. In that case, but yeah, just putting it out there, right? So a lot of time people would say like it's schemaless, which is not true in all cases, right? It still has schema, but you verify the schema on read basically. So when you're trying to convert it into a particular type of object, right? So even if you're using a NoSQL, you would want to like basically serialize into an object, right? You would not be using it. It might be just an object, but it's still is an object, right? Something in some structure, right? You would want to serialize in some structure. If that serialization doesn't work out, then it will not work out. Your application will fail at the point of time. So it's not schema-less. The difference is SQL checks or SQL is basically checking the schema on write, whereas NoSQL basically on read you would want to verify the schema or things like that. Is it clear? There are other differences also, but I just wanted to put it out there. Yeah. Okay. So I think, yeah, Venkatesh, yeah, go.
This is a general one. In a distributed system, mainly how the security and all, how we can handle this. Going to be asking any interviews how.
Yeah. So I think we'll discuss this on when we discuss about security also, right? So we're going to discuss this, but yeah, I mean, you can think about this, right? A lot of security is a very generic topic and it applies to SQL, NoSQL, or any kind of thing, right? It is, I would not say that just because you're using a new NoSQL, you'll have to add more security. That's not the case. I mean, it's going to remain the same, irrespective. So I would say, irrespective of your database choice or your application choice or whatever if you're using third party, then probably you'll have to be careful because a lot of things might go wrong, whether you're sending encrypted data and all of those things might go wrong. But I would say that once you're using a database and things like that and how you're interacting to it, it does not depend on the type of database you're using. So if you're saying that because I'm using NoSQL, will somebody ask me more questions on security? Not true. If there are security things or if the application which you're trying to build has sensitive data, no matter who you use SQL or NoSQL, you will get the same kind of questions about security. So there's nothing special which you need to do for NoSQL. There are things which you can always do about security is write encrypted data. You can encrypt data at the database or at the table or at some level, or like you can encrypt the whole database as such. Whereas you can do is like you can encrypt it at a row level or some record level as such. But we'll probably come to that later. Let's not focus it right now. When we discuss about security, then we'll discuss this. Okay. Yeah. Okay. So I think we're close to time, but I just wanted to take a feedback at this because, to be honest, LLD is something which it's a bit difficult to comprehend, and I expect people to practice more and then to understand the whole concept. But HLD is something which I would want you to understand it on the spot. I would say that if you're not understanding anything at this point of time, please ask me questions, ask me for examples, and ask me for things like this. Because if you don't understand right now, even reading 10 kind of things, you might get like, and this is also something like if you read 10 books, you'll get 10 different concepts of it, which where it might mean the same thing, but you might also get like, there's a lot of detailing things which you'll get, and you will basically, it will deviate you from the actual fundamentals of it, right? So I would say if you don't understand anything at this point of time, feel free to ask questions, ask for more examples, and ask for things like that, right? So yeah, Sumit.
So apart from the material and the lectures that are there, definitely I would want to go through them again, 100%. But apart from this, what other material should I refer to? Like anything you can suggest?
Yeah, so if you guys like heavy reading, I would say, so this is where I would say, okay.
Or like practice questions,
Yeah, so practice questions we are going to discuss, and I'm going to give you a list of questions which we'll be doing, right? The only reason for not doing it right now is because I want to cover all the topics first, and then I want to discuss about those practice questions, right? Because if you don't understand, like why do you use distributed systems and how deployment works and things like this, right? It's going to be difficult for you to answer those questions. Now, what you're doing is reading a question, you're trying to understand a concept, which is not a great thing, to be honest. If you understand this concept, right? If you understand where to use, if you understand SQL, NoSQL, and you understand the trade-off between them, then when I'm discussing a use case, you'd be like, okay, why should I should use a SQL here? I should use a NoSQL here. It makes it more clearer for you, right? So that's the reason I'm not discussing the questions as such. I'm going to share with you guys a list of all the questions which I feel as a commonly asked questions and things like that. And probably they would also have like a sample solution and things like that. So you can just read on your own. But yeah, that would come sometime later in the course, I would say.
Sure. Thanks, Sidhu.
Yeah. And in terms of books, right? I have read 2 books which are good. One is designing data intensive applications. But I would just I will be honest with you, that's a heavy read that has a lot of different concepts that goes into a lot of different details, which I would say you should read. I would not say you should not read, but at this point of time, because I mean, I would say like, so I'm always in this approach, right? When you're learning something, learn the breadth first. Learn these things. Like there would be 10 different topics. You learn all of these. Once you're familiar with the top level topics, then you can pick and choose, like, okay, I like all of these things. Then you can go deep into this, right? So it should be something like this. So right now I'm trying to talk about these things, not going into like these things as such. And probably I don't think so we'll be able to cover all of those things in this course, to be honest. But I would want you to do at least these things well. Once you have done these things and you understand the basic, then you can go ahead and read those books, and probably you can get a sense of all of these also, right? So the book name is Designing Data Intensive Applications. And that's a heavy read, I would say. It's gonna take you time to read one page. Even one page to read and comprehend would take some time. It's not simple read. It's gonna be like 700 odd pages of that book, but it's gonna take you some time to read those things, right? So I think 700 or something. And don't worry, I would say even if you go through it once and you don't understand much, it's fine. Just skim through that book, come back, or while skimming through marks few topics, saying that okay, I need to revisit this. Come back to it after after you've done the first pass. Go back and read those topics. If you still need another pass, I would say like if you go through this book in 3 passes, right, or you would be fine. But you'll need that 3 passes, and this is 700 pages book, so it's gonna be hard. And whenever you read about this, one way to do this is for each individual topic, go ahead and try to read all the resources possible on the web. I would not recommend that. Read something. If you don't understand it, mark it down, come back to it and try to understand this. If you find something relevant, okay, read it, but don't go too deep into any of this topic, because either you'll lose motivation understanding that one topic, or you go so deep into one topic that you have messed out on all the other topics as well. So take that 10 pass or the first pass itself and then read it as well. This is one of the books. The other book is Database Internals, but I would say only for people who are very interested in this can go into this. I think everybody should try to read this, but not a hard requirement, I would say. And don't think of this book would help you to clear interviews straight away. These concepts are good, but in most interviews, you probably not use a lot of these concepts, to be honest. If you know this, obviously it's fine. If you're interviewing for a very senior role, like an architect kind of a role, or a very senior staff or things like that kind of role, probably this book is going to be useful. But if you're interviewing for a mid-level or a senior role, or something like I would say 5 to 10 years of experience, probably you would not use any of these concepts. Most of these concepts in the book, you probably not, even if you don't know about this, you're going to be fine. So you can read this and this. Apart from this, there's a GitHub resource called as System Design Primer. And I'm going to send this in the group. Primer. This is a GitHub. Somebody has created this, and I think Don Martin or something, this the guy's name is. It's a very good resource. It's not very deep, but it will cover all the topics that you need to use. And I use that as a reference. So what topics I need to cover is, I'm using that as a reference as such. So if anybody wants to use that, you can use that. Okay.